Wireless communication systems are a driving force for connecting our world. The third and fourth generation wireless communication systems brought forth the mobile internet, which changed our society. The fifth generation and beyond 5G systems will also bring their share of society-changing technologies like mobile, virtual, and augmented reality made possible through high-speed fixed wireless broadband connections. Moreover, in the context of the 2020 pandemic crisis, the interest in increased connectivity goes well beyond entertainment applications and towards population-wide distance learning and widespread home office programs. This technological evolution goes along with a continued increase in demand for higher throughput, lower power consumption, and more scalability for all parts of the system, including the baseband signal processing on the physical layer. In terms of throughput, for example, requirements that go far beyond the tens of gigabits targeted in the 5G standardization are foreseen. A major source of complexity and power consumption in baseband signal processing for wireless communication systems is the forward error correction. An efficient forward error correction is therefore crucial for reliable communications. In 3G and 4G standards, turbo codes were adopted as forward error correcting codes. Indeed, for standards like UMTS, which only required a throughput of 1 megabit per second in its 1999 release, to LTE, which required 100 megabits per second in the 2008 release, turbo codes, with their excellent error correcting performance for the targeted error rates, built-in code rate flexibility, and ease of encoding, were a perfect match. Turbo codes are also used in the current and future releases of LTE Advanced Pro, which requires a throughput of several gigabits per second and supports almost 200 different frame sizes and a wide range of code rates. In terms of error correcting performance, contributions to the 5G new radio standardization showed turbo codes at least on par with the contending code families of low-density parity check codes and polar codes in this regard. Despite these improvements and their advantages, turbo codes were not adopted in the 5G new radio in favor of LDPC and polar codes. One contributing factor to this decision is that this family of codes has been seen at a disadvantage for high throughput applications because of the inherently serial nature of their decoding algorithm as opposed to the inherently parallel belief propagation decoding of LDPC codes and the low complexity successive cancellation decoding of polar codes. Both LDPC and polar codes can be decoded with several hundred gigabits at the cost of flexibility and coding gain, while most state-of-the-art implementations for turbo decoders achieve less than 10 gigabits per second, a throughput gap of several orders of magnitude. Indeed, at the time of the choice in 3GPP, state-of-the-art turbo decoder implementations exhibited an area efficiency of 1 to 2 orders of magnitude worse than optimized LDPC or polar decoders for high throughput. However, despite this drawback and for swift deployment purposes, the 3GPP Standardization Committee submitted its 5G solution to meet the IMT 2020 requirements based jointly on the evolution of LTE and on the first 5G new radio specifications. The underlying idea was the upgrade towards an LTE evolution-based 5G solution before and during the more costly 5G new radio deployment in the next years. Being the forward error correction solution of LTE evolution, the need for high-throughput turbo decoders that allow for rate and frame size flexibility becomes a short-term need. This, however, is not practically feasible with current turbo decoder hardware architectures, which merely offer a maximum throughput in the order of single-digit gigabits per second or require large amounts of chip area. To summarize, an important effort is needed to achieve area-efficient high-throughput turbo decoders while keeping the inherent advantages in terms of flexibility of this code family. The higher area efficiency of high-throughput LBC and polar decoders comes at the cost of a deficit in flexibility with respect to code rate and frame size. Most of the turbo decoders are highly flexible with respect to frame sizes or can be made flexible. However, when supported with the classical BCJR decoding algorithm, this flexibility represents one of the main factors that lead to the reduced efficiency of turbo decoders. The consequences are twofold. First, there is a high potential for lowering turbo decoder complexity for applications with limited flexibility requirements, and second, for applications requiring high flexibility such as mobile broadband, turbo codes can be superior to LDPC or Polar codes if the factors limiting the achievable throughput for hardware implementations can be overcome. The road to terabit per second turbo decoders goes through the joint introduction of profound modifications to their decoding algorithm and to their code design, while taking into account implementation and application constraints. In fact, the BCJR or SOFA-based algorithm offered excellent performance while being able to keep up with the throughput requirements up to a few gigabits per second, but for higher data rates, the effort was mainly focused on LDPC codes and the more recent Polar codes because they seemed easier to parallelize. Meanwhile, major modifications were proposed for these code families towards increasing throughput efficiency. We can clearly cite here the various simplifications of check node processing for LDPC codes, in addition to the structural code design modifications towards more regularity and periodicity, such as the introduction of the quasi-cyclic nature of their parity check matrix. More than 30 years after their inception, it was the work of Neal and McKay and the advent of turbo codes and iterative processing that sparked academic interest in LDPC codes. On the other hand, it was not until the publication of the landmark paper of Tal and Vardy and the subsequent addition of cyclic redundancy checks to SC-list decoding 4 years after the discovery of Polar codes that they were put on equal footing with the previously unchallenged LDPC and turbo codes in terms of error-correcting performance. Moreover, despite the intensive academic interest following the above-mentioned advancements, it took in both cases another 8 years before those codes made their way into standards. These examples illustrate that the age of a code family is not on its own a meaningful metric for potential. Therefore, revisiting the 27-year-old turbo codes with nowadays advanced knowledge and techniques, in particular recent advances with respect to code and decoding algorithm design, as well as decoder hardware architectures, can have the potential to transform this code family to appealing contenders for future standardization. The factors limiting the achievable throughput for turbo decoders are of different nature in relation to the code design, decoding algorithm, and hardware architecture, and they can be overcome only if investigated and considered jointly to make the leap across the throughput gap. In order to make the leap across the throughput gap, 3 main challenges have to be addressed en route to viable high-throughput solutions for beyond 5G applications. First, further improvements in area and power efficiency are necessary. In addition, enabling the support of frame size flexibility as well as the support of medium to large frame sizes of several thousand bits are crucial to preserve the large coding gains provided by turbo codes. Providing solutions to these 3 challenges is at the heart of the 5 objectives of the TurboLEAP project. Objective 1 aims at improving the area efficiency of turbodecoder implementations. Best previous turbodecoder implementations featured in the state-of-the-art are based on the PMAP and FPMAP architectures, and they achieve an area efficiency of less than 3 gigabits per square millimeter, while their LDPC and Polar counterparts achieve tens of gigabits per second per square millimeter. The prime objective of TurboLEAP is to close this gap by improving the area efficiency by around 2 orders of magnitude. To achieve this ambitious prime objective, all tasks of all work packages within TurboLEAP implicitly target this objective, and technical decisions will be made favoring improved area efficiency. The second objective is the improvement of the power efficiency of turbodecoder implementations. The candidate decoder hardware architecture for achieving the targeted improvements in area efficiency and throughput is the fully pipelined iteration unrolled turbo decoder architecture or UXMap architecture. Investigations and subsequent improvements and refinements of the power efficiency of this decoder architecture are necessary in order to find solutions competitive with respect to LDPC and Polar decoders. Objectives 3 and 4 target a throughput of 1 terabit per second for medium and large frame sizes up to a few thousand bits. On top of that, Objective 5 is to demonstrate a hardware implementation of a decoder for spatially coupled turbocodes. By pursuing these objectives, TurboLEAP aims at making substantial contributions towards decoding turbocodes at terabits per second with current silicon technologies, closing the large throughput gap to LDPC and Polar codes. Moreover, this goal shall be achieved while providing considerable frame size flexibility and while keeping most of the major advantages of turbocodes like the built-in rate flexibility.